Welcome viewers and subscribers. Welcome back to another video. I trust that everything is good with all of my precious viewers and subscribers. So in today's video, I am going to teach you how to calculate the maximum bending moment for a fixed end beam. Now I have stated to you in a subsequent video that a beam exists with two different type of condition. So the first thing you must observe as an engineer, the end condition of your beam. So your beam can either be simple supported or your beam ends can be fixed. As in the case of the cantilever video that I've shown to you, I think 2 or 3 videos prior, is that you will observe that one end of the cantilever is fixed and the other end is free. So in this case, we have both ends of our beam that is fixed. Now, you will mostly find a fixed end beam in what is known as a frame structure. So there are two types of structures. There are load-bearing structures and there are frame structures. So a frame structure is a structure or a building that is built primarily of columns and beams. So if you see a building being erected primarily with a series of columns and beams, that structure or that building is going to utilize what is known as fixed end beams. So those structures are used to carry heavy loads. So you will see your commercial building or your industrial building being built with a frame structure. So a fixed end beam looks something like this, with both ends of the beams are fixed. Both ends of the beam is fixed. So when either end of the beam is fixed, it is going to cause a moment. So we're going to have a moment here, and we're going to have a moment here. So this moment is tending to turn the beam in the anti-clockwise direction. So we usually denote anti-clockwise direction with a minus. And since this end here, the moment is turning the beam in a clockwise direction, we denote clockwise direction by a plus sign or a positive sign. Now, as you can see, this beam is being loaded uniformly. So there's a uniform distributed load on this fixed end beam. And the formula to calculate the fixed end moment for a fixed end beam is a fixed end beam with a UDL or uniform distributed load is known as WL square over 12. So WL square over 12 is what we use to calculate the moment for a fixed end beam with a uniform distributed load. So if you should look at the drawings to the right on my board, this is a fixed end beam with a point load, right? So if you should observe again, you have from this end, the fixed end, towards the point load, we dimension that as A, and from the point load to the opposite end, we dimension that as B. So to find the fixed end moment for AB, the formula is the load times A times B squared over L squared. So the fixed end moment to find AB is P times A times B squared over L squared. Now, to find the fixed end moment BA, the formula for that is the load times A squared times B over L squared. So if you observe, you will have noticed that when we are finding the fixed end moment for AB, we square B. And when we are finding the fixed end moment for BA, we square A. So in this case, B is being squared, and in this case, A is being squared. So that is how you find the moment for a uniform distributed load on a fixed end beam and the point load on a fixed end beam respectively. I am going to show you how to calculate the fixed end moment. So the fixed end moment, so the first moment that we are going to calculate is fixed end moment AB. So fixed end moment AB, the formula is going to be minus PA B squared over L squared. And the reason for using the minus sign here, remember I've stated to you that because the moment at A here is turning the beam anti-clockwise, and we denote anti-clockwise as a sign convention using the negative sign. So the moment here at A is going to turn the beam negative in an anti-clockwise direction, and the moment at RB here is going to turn the beam clockwise in a positive direction. So the fixed end moment for AB, so we have fixed end moment AB is going to equal to minus P, and minus P here is 1,000 pounds. 1,000 pounds. And I should have, before I go into the calculation, just explain what the beam system here is doing. So this beam system here has 1,000 pounds coming down on it, and it is 30 feet from reaction A here, and it is 10 feet from the reaction B here. And the beam has a span of 40 feet. So we are going to calculate the fixed end moment for A and for B, and then we can calculate our reaction, plot our shear force and our bending moment diagram, and come up with the value for our maximum bending moment for this beam system, this fixed end moment beam system. So we have here fixed end moment AB, so the load coming down is P, and P is 1,000 pounds. So we have a minus 1,000 pounds because the A is turning the beam in a negative direction, in a clockwise direction. So we have minus 1,000 pounds, and the dimension for A is 30 feet. So we have 30 feet here times B, and B is 10 feet square, so B is 10 feet, 10 feet square all over 40 feet square. And if you should plug this into your calculator, you're going to end up with minus 1,875 pounds foot. So the moment at A here is going to equal to minus 1,875 pound foot. So that is our moment, our fixed end moment for AB. So now that we have calculated the fixed end moment for AB, I'm going to calculate the moment, the fixed end moment for BA. So the fixed end moment BA so the formula to calculate fixed end moment BA is the load times A squared times B over L over 2. So we have the load here, and this time, if you observe, we are not using the minus sign here, as in the case of AB, because at BA, the beam is turning in a positive direction. It's turning the beam in a clockwise direction. So we do not have to use the minus sign. So we're going to use the sign convention here as a plus. So this is going to be 1,000 pounds times A squared. So we're going to square A now, and A is going to be 10 feet square times B, and B is 30 feet over 40 feet square and if you should plug 1,000 pounds times 10 feet square times 30 feet divided by 40 feet, you're going to get 5,625 pound foot for a fixed end moment at PA. So there you have it. So the moment at AB is going to equal to 5,625 pounds foot. So there you have it. The fixed end moment for AB is minus 1875 pounds foot, and the fixed end moment for BA is going to be 5,625 pounds foot. So I'm going to show you now how to calculate the reaction as well as the bending moments and the shear force diagram. I'm going to show you how to calculate the reaction, but before I proceed, there's a small error in my calculation. The result is going to remain the same, but this here should be our 10 feet, and this here should be our 30 feet. 30 feet squared, and the value is still going to be 5,625 pounds foot, because you know A is going to be 30 feet and B is going to be 10 feet. But instead, in the first instance, we square the 10 feet here, and in the second instance, we have to square the 30 feet here. So, having shown you that, I can now move to calculate my reaction. So, to calculate the reaction, I'm going to calculate the reaction of B first. So we are going to take moments at A, at RA. So we have RA here as our reaction here going upwards, and we have RB here as our reaction going upwards as well. So to calculate the reaction for RB, we're going to take moments at RA. But remember what I've said to you in my previous video, wherever you're taking moments, that position is going to be 0, because the force is going to be 0 and the distance is going to be 0. 0 times 0 is 0. So there's going to be no moments, and moments, as I said to you before, is force times distance. So we're going to take moments at RA. So the summation of moments at RA is going to equal to 0. So we're taking moments at RA, but in taking moments, the first thing we observe is we have a moment here of minus 1875 pounds-foot. So our first moment is going to be minus 1875 pounds-foot. Plus, we can now take our moments here at this end, which is 5,625 pounds-foot. So it's going to be plus 5,625 pounds-foot plus the reaction here. The reaction here at B. Now we're not going to move the reaction at B here. So we have 1,000 pounds here. There are 1,000 pounds here coming down, and this 1,000 pounds is acting 30 feet away from RA. So the next moment is going to be plus 1,000 pounds times 30 feet. Right? So we have dealt with the moment here at A. We have dealt with the moment here at B. We have dealt with the force coming down of 1,000 pounds acting 30 feet away from RA. So the next force we have to deal with now is RB, and RB is going upwards. So RB is acting 40 feet away from RA. So this is going to equal to RB times 40 feet. So we're going to solve for RB. So in solving for RB, we're going to, if you should plug this into your calculator, let me do it for you. So we have here minus 1875 plus 5625, right? That is going to equal to 3,750 pounds-foot plus 1,000 times 30, that's 30,000, plus 30,000 pounds-foot. So we're going to make RB the subject of the formula. So we're going to divide this now by 40 feet equal to RB. So if you should add 3,750 plus 30,000 and divide by 40, the result should be 843.75 pounds-foot. Sorry, pounds. Sorry, pounds. Pounds equal to RB. So the reaction at RB is going to equal to 843.75 pounds. See that? So in a short way, how to find the reaction at RA, you can go back and you can take moments at RB and do the same thing to find the reaction at RA. But I have given you a demonstration of that in my last video. So in this video, I'm going to take a shorter route to determine the reaction at RA. So to determine the reaction at RA, I've said to you multiple times that the forces that are going downward on the beam must be equal to the forces that are going upwards on the beam. So if you look at the beam here, the beam system here, we have 1,000 pounds coming down and we have RA and RB going up. So the summation of RA and RB must be equal to 1,000 pounds. So if you notice, we have the summation of forces coming down must be equal to the summation of forces going up to satisfy equilibrium, right? So our forces coming down is 1,000 pounds. So we have 1,000 pounds. And we have RA going up and RB going up. So we have plus RA plus RB. So 1,000 pounds must be equal to the summation of RA plus RB. So we have here 1,000 pounds equal to RA plus, and we have just calculated the reaction for RB. So RB is 843.75 pounds. So RA, we're going to solve for RA now. So RA is going to be 1,000 pounds minus 843.75 equal to RA. See that? So 843.75 from 1,000 is going to be 156.25 pounds equal to RA. So the reaction at RA is going to be 156.25 pounds. See that? So now I can now plot my shear force diagram and my bending moments diagram. So to do that, our shear force diagram is going to look something like this, and this is our zero line here, our zero line shear force. So if you notice now, we have here 156.25 going upwards, right? And 1,000 pounds coming down, and we have 843.75 going up. So in plotting your shear force diagram, the shear force diagram is just a demonstration to show you as the design engineer how the force is being distributed along the beam. So we have here going upwards 156.25 pounds. So we draw our arrow here going up, and this point is 156.25, and nothing happened here, so we carry this line across here. But to this point here, we have 1,000 pounds coming down. So if we have 1,000 pounds coming down, it's going to push the beam downward, but from here to here is already 156.25. So this 1,000 pounds here is going to push the beam 843.75 pounds below the zero line. So 843 is going to come, imagine 843 is going to come here, 843.75. I notice 843.75 plus 156.25, we get back our 1,000 pounds. So since nothing happened here, nothing happens here, we come back to our 843.75 here, and we have a force now, a reaction of 843.75 going upward again. So you see, my beam, the shear force diagram closes. And how we determine that our shear force diagram is closed correctly, the force here of 843 is equivalent to the reaction of 843.75. So we have 843.75 here and 843.75 right here. So our shear force diagram is correct. And as I mentioned to you before, if you're plotting your shear force diagram and you do not get your shear force diagram to close, you do not get this load here to equal to this load here, you have done something wrong and you need to recalculate again. So our shear force diagram will look something like this. Now our bending moments diagram, I don't have enough space, but I'm going to see if I can fit it in. Our bending moments diagram now is going to be the area of these two, of one of these two rectangles. So we're going to choose the maximum. So we have here area 1 and area 2. So we have area 1, which is going to be 156.25 times this distance. So this distance is going to be 30 feet. 30 feet times 30 feet equal, and then we have area 2, which is going to be 843. 843 is going to be the height here, 843.75 pounds, times the distance, this distance which is going to be 10 feet. So this distance is 10 feet. 10 feet plus 30 feet, we get back over 40 feet. So this is going to be 10 feet. So right away I can tell, like, to move one decimal place, this is going to be equal to 8, sorry, it's going to equal to 8,437.5 pounds foot, and this is going to equal to 156.25 times 30. This is going to equal to 4,687.5 pounds foot. So we're going to choose the higher, which is 8,437.5 pound foot to be our maximum bending moment. So our bending moments diagram is going to look something like this. Since it's a point load, and the maximum bending moment is going to be 8,437.5 pounds foot. So this is going to be our maximum bending moment for this fixed end beam. So to design this beam, the engineer is going to plug this in his formula to calculate the reinforcement to go into this fixed end beam to withstand the 1,000-pound load. So that is it for this video. The next video, I'm going to go into a actual beam design, a simple supported beam, where we're going to factor our loads and we're going to take into consideration the beam self-weight, and we're going to calculate our reinforcements in the beam. So as usual, you know what to do already if you're a regular viewer or a subscriber to this channel. In the event that someone is watching my channel for the first time, I'm asking you to subscribe to the channel I'm asking you also to hit the thumbs up button and give me a like, and I'm going to catch you in my next video. So take care of yourselves. Thank you.